יזדי וצללי פה. יזדי וצללי פה.
Hello. All right. So on Sunday, we have reached some postulate about maximal entropy principle. Entropy principle. Okay. And what this maximal entropy principle says, that the equilibrium value of any unconstrained internal parameter is such to maximize the entropy for the given value of the total internal energy. Okay, so in simple words, what does it mean? So if you consider a system of molecules, if you consider a system of molecules that are all red, and if I have some sort of a unconstrained internal parameter, what I mean by unconstrained parameter. So there is a bar that can move to the left or to the right. Okay. So the position of this bar, x, is unconstrained. I haven't constrained. I haven't set it to a specific value. The maximal entropy principle says to us that if we consider that the total energy of the system is constant, so E is constant, okay, the position x that we should choose, okay, in equilibrium, the system will do something that the molecules, they have thermal energy, so they will bounce on this wall. The wall will move to the right, it will move to the right or to the left. There should be some dynamics, but what is the equilibrium state? So the maximal entropy principle says to us that in equilibrium, x is such that the total entropy of this system is maximal. Right? So if you would try and plot this, so let's consider that this is E, okay? This is S, and this is our X. Two. So this is S, this is E, and this is X. Now, as a function of E, S is always growing. So S, but it can obtain different values for different values of X. So in some sense, S looks like what? This way. So S is a three-dimensional sphere. Okay, so this, that. Okay. So imagine that this is a three-dimensional surface, and S is growing as a function of E. Okay. On top of the surface, each point is a specific point of E and a specific point of X. Right? Now E is constrained, so we are saying E is actually constant. So we have to make a cross section which is parallel to X. So basically, we are taking a cross section out of for a specific E, which is parallel to X, okay, and parallel to S. Okay. Now, if we look on this cross section, and we look on this cross section, how S is modified as a function of X, the maximal principle tells us that there should be a maximal point. This is a function of X. And this is S. An equilibrium is achieved at some given X star such that S of X star is maximal. So this is the maximal entropy principle. If you have unconstrained parameters inside the system and you let the system live, B, it will eventually thermalize, it will reach an equilibrium state. And how you choose what is my equilibrium state? Well, this is the state where all your unconstrained parameters are such that S is maximal. Now, this is some kind of a postulate, right? But it's a little bit difficult to grasp because we don't really know what entropy is. Yes?
Is it like a maximal point or the maximal point?
The maximal point. The. Not local, global.
Oh. Okay.
Global. The principle is that the system will eventually find such a point where it's in a global maximum.
But there are like two bistable systems.
So what you're saying is there are two exactly points which are maximal, right? For example, yeah. So usually they are going to be separated by some infinite barrier, and it will take you an enormous amount of time to go from one to another. All right. So this is. Any other questions? Yeah.
This is all assuming constant energy?
Yeah. E is always constant.
Okay.
It has to be constant. Now we turn this around. We can say, what if S is constant? Bad. What if S is constant? Okay. And we have some X unconstrained parameter. And we want to find E at equilibrium. So I'm asking the following question. There is a maximal entropy principle which is some kind of a postulate. Okay? What is, if I turn my life around, I don't want to speak about entropy because I don't really know what entropy is. I can send you a very nice YouTube videos about it, but I don't really know what entropy is. Okay? But I don't know what's energy. Can I somehow transfer this principle into a principle about energy? Yes.
זה עכשיו כאילו מקרה אחר?
No. So the question is this some different case? you can consider it the same case, but I'm now saying E is free and S is constant.
Okay.
Right? Great. So what do I do for that? So first of all, I know the following, that at equilibrium, ds to dx of E equals 0 because it's a maxima. Moreover, d square s to dx squared with constant E is smaller than 0. Okay. Why? Because it's a maxima. So it's a maxima, it's an extremal point. This is why the derivative is 0. And because this is a maxima, the second derivative is negative. Yes?
Technically, would the second and third derivative be...
Forget about it. Forget about it. Usually this is enough, right? When you studied analytical mechanics about maximal action, you never said anything about this part. You always said a lot of stuff about extremal points. Okay, so I want to show what happens to the energy. So let's start. So first of all, of course, we know that S of E and X is constant, okay, which means that ds to dE x dE plus ds to dx with constant energy dx equals 0. Great. I can do the following trick. I can say that dE to dx, if you want, I just divided the two parts, or I used a theorem, but d to dx is minus ds to dx of E divided by ds to dE of x. Okay. Out of this comes this. You can say, well, Stas, you just divided, or I can prove it to you formally. Okay. The moment that we know this, let's define the following quantity. P is D. This guy, let's call it P. Okay. Now, what we want to show, that E at equilibrium attains something. Right? It's a point which is, we want to show maybe it's maxima or minima. So we want to look on this one. Okay. So P, according to this, equals to minus ds to dx with constant energy divided by ds to dE with constant x. Okay. What is ds to dE? Is 1 over t. Right? So we have here minus t ds to dx with constant energy, and at equilibrium this equals 0. Right? So we know that at equilibrium dE to dx equals 0. So all right, great. It can be minimal, maximal, or something else. This external point, that's already good enough for us. Now let's see what happens to d squared E to dx squared at S. Of course, this has to have S already. So what do we have? So this is dP to dx at constant entropy, which is dP to dE to dx. This is x, this is s, plus dP to dx, this is E, dx to dx. Yeah.
הפרמטר הזה P זה הלחץ, כמו שאנחנו מכירים אותו, או שזה סתם פרמטר קראת לו P?
So P for now is just some parameter, some variable, but it's actually, if X is V, is going to be pressure.
ולמה קבעת שהוא 0 בשיווי...
In equilibrium, well, because ds to dx is equal to 0 at equilibrium.
אוקיי.
Right? So this is we proved from the maximal entropy principle.
כן, כן, זהו.
All right? And then we used it. Okay. So when we have this, the next step is, what is this? So we have dp to de, that's we keep exactly the same. D to dx is what? Is p. dp to dx, we keep it exactly the same, and dx to dx is 1. Okay, so in total, what we have, dp to de, with constant x, multiplied by p, plus dp to dx at constant e. At equilibrium, this guy, p, is equal to 0. So all we're left with is dp to dx with constant energy. What it is? Something nasty. It's d to dx of what? Of this guy. Right? dp to dx minus ds to dx of e divided by ds to de of x in total. What it equals to? So we have minus d squared s dx squared at e divided by ds to de at x plus ds to dx d squared s dx d divided ds to de squared, and it doesn't matter because at equilibrium this is simply 0, right? Because ds to dx at equilibrium is 0. This guy goes away. And finally, we reach what? We have over here, ds to d is 1 over t. So this is minus t. d squared s to dx squared at constant energy. But what is d squared s to dx squared at constant energy? It is smaller than 0, right? So we have a quantity which is smaller at 0. We have t which is always positive, okay? And we have, because it's a derivative of energy with respect to entropy, and it's a monotonically growing function, so t is always positive. So we have positive, negative, negative. In total, this is positive. In total, this is positive. So what we have now, we now have energy minimum principle, right? So we all heard about it, and here we have seen the proof. Energy minimum principle. The equilibrium value of any unconstrained internal parameter is such as to minimize the energy for the given value of total entropy. Okay. So we keep entropy constant. We have something that can vary, and this something has to choose a very specific value. And at this value, how we choose it? We choose it by looking on the minimum of energy. So if we're going back to this description, we have this two-dimensional manifold, okay, of S, which is a growing function of E, okay, and it somehow behaves as a function of X. Okay. So if previously I've looked on what? On a constant slice where E was kept constant, now what I'm doing, I'm slicing this stuff not in a way that it's parallel to S and X, but in a way that it's parallel to E and X. Right? So the slice is going to be like this. Okay. So when I now look on the slice over here, the equilibrium is going to be X star E X star, which is minimal. So those two principles are the leading principle that I can use in order to decide what is my equilibrium state. Of course, if everything is constrained and nothing can move, okay, well, this is the state. But usually I have some parameters that are somehow free. Okay? And what I decide, what is my equilibrium state? I decide it by choosing a maximal value of entropy or a minimal value of energy. So for example, if my energetic landscape looks like this, so this is a position of my particle, this is the energy of the particle, it is not conserved, okay, so this is not the classical mechanics, so it can vary. Why it can vary? Because there is an interaction between this particle and the outside world, so its energy is something else. So if this red dot or the red circle is it's actually my particle, from classical mechanical perspective, what I expect is, well, you have a total energy, right? And the particle is going to roll down and roll up and roll down and roll up. Okay. In reality, when there is no conservation of energy, so I actually can go above any specific limit and be over here and be over there. So the system, the particle, can move swiftly from one side to the other. Where is my equilibrium? Equilibrium is when my particle is at a minimal energy over here. Okay. It does not mean that the particle cannot be at any other position. The energy that I'm talking about over here is in some sense even not the average energy, but the energy of this preferable state. And the preferable state is the state of minimal energy, and the particle will be over here. If I look on the system as a function of time, okay, so if I plot x as a function of time, this is my position. This is time. This is the position of my particle. It will do something like this. But the preferable energy and the average energy is going to be this one. This is the equilibrium. It will fluctuate around it, okay? But the equilibrium is defined by this value over here. Yes?
In the minimal energy principle, you proved that the energy is a as like a local minimum. So couldn't the equilibrium state be the second?
Yes. So A, you're right. I proved only that it's a local minimum. It can be extended to a global minimum by using concave and convex properties of different functions. But the general assertion that it's going to reach global minimum.
Okay.
I haven't proved it. I just saying it.
Okay. I believe.
Don't believe me. Believe nature. Any other question? Yes.
בעצם בפיתוחים האלה, פעם אחת אמרת שהאנרגיה קבועה, פעם שנייה אמרת שהאנטרופיה קבועה. עכשיו, זה שכאילו בוא נגיד, העיקרון של... הנקודת מינימום של האנרגיה, אוקיי? היא רק כאשר S קבועה, אלא כאילו או... כל מצב בעצם.
So, the question is where and when I find this minima or maxima. So whatever I told you is only when S is constant, then I have a minimum, right? Only when energy is constant, then I have a maximum. Right? I have to constrain the system somehow. If E can be whatever I want and S can be whatever I want, there is no principle. All right, so some definitions that you probably have seen and we will also see in the future is, and we are going to use it in this class, and I think it's worth mentioning, is, for example, heat capacity. So, definitions. Heat capacity. Usually it's by the letter C, and it's equals to dQ to dt. Basically, we can say, well, if you're going from one equilibrium state to another equilibrium state, we can simply say that this dq is d ds divided by dt. Okay, so this is C, and generally speaking, we replace this ds to dt to a partial derivative. So we have C of f when t dou s to d dou t with a constant f, and we can have C of x where we have t ds to dt with a constant x. So examples that you have probably seen in the class on thermodynamics is Cp and Cv, right? So you have seen that Cp, it is what? Is t ds to dt with constant v, and we have Cv, it's t ds t with constant v. Another quantity that you also heard in the class on thermodynamics is the chemical potential. So what is a chemical potential? The rate of change. So if I have N1 number of particles of type 1, and N2 is type 2, and Ni is type I. So mu I is the rate of change of the total energy of the system with respect to number of particles, Ni. So this is chemical potential. It basically it says that, well, how then I introduce additional particles or I subtract the amount of particles from the system, the energy is modified somehow. How exactly it's modified? Well, it's modified due to the chemical potential. So, in general, I can say that dE is TdS. If we have a pressure, external pressure, so it's minus PdV. Okay. And we have plus mu1 dN1 plus mu2 dN2 plus mu n dN. This is our energy. We say that it's an equation of state, meaning that it depends only on the equilibrium state of the system. I measure it for the equilibrium state of the system. And the natural coordinates or variables of this function is s, v, and 1, and 2, and n, and etc., etc., etc. Okay. So E is a function of entropy, volume, and the composition numbers. Composition numbers are the number of different particles that we have inside the system. Great. Yes.
אפשר שוב הסבר למה זה בדיוק הפוטנציאל הכימי הזה?
So the chemical potential is, the only explanation that I can give you is the rate of change of energy with respect to the number of particles. No more than that. We will learn a little bit more when we study thermodynamical potentials. But for you is by how the energy is modified when I change the number of particles. That's it.
Okay.
אפשר גם שאלה?
Yes.
לגבי העיקרון של המקסימום אנטרופיה, בשביל האינטואיציה שלי, אמרנו, במצב שבו האנטרופיה מקסימלית, אני בתוחלת תראה את המצב שהאנטרופיה מקסימלית, כאילו זה נכון? או שתמיד אני לא אותה באנטרופיה מקסימלית?
So the question when I am at maximal entropy, and the answer is so me and you are probably not in the maximal entropy because we are not in equilibrium. So you take a system, you wait a while, the system equilibrates, it will come to equilibrium, and all the different internal parameters that can vary, not that you keep constant, but all the different parameters that can vary, okay, are going to be at such values such that the total entropy is maximal. So in equilibrium, the entropy is maximal, right? That's the claim. When you wait a little bit, the entropy is maximal. Okay. Any other questions? All right. So when I look on this function, I say, if I know what energy is and how it is modified with respect to entropy, volume, and different number of particles, I can explain everything, right? This defines my state. My claim is that there is, for a specific S, a specific V, specific values of n's, there is only one specific energy, right? So when I modify something or some of those parameters, the energy is going to be also modified. And by following how this function is modified, I can know or predict what will happen to the system, what will happen to its energy, how the system is going to evolve from one equilibrium state to another. For example, I take the entropy and I add to it a specific value. By how much the energy is going to change. Okay. So if I know this function, in principle, I can predict whatever is going to happen to the system. When I'm saying happen to the system, if I modify something, wait a while, let the system equilibrate, I can predict to which equilibrium state the system will evolve. What is the problem here? Who knows what entropy is? How to modify entropy? How I control entropy? I don't really know how to control entropy, right? Nobody really knows. So this is a very nice description, but in some sense it's useless for us or useless for your favorite experimentalist because we don't know how to control entropy. Yeah, well, maybe we can a little bit heat the system, but I don't want to heat the system. I want to study or look on this equation not as a function of those coordinates, those variables. I want to use variables that are actually controllable in a lab. S is not controllable in a lab. Okay? I need some other values. So let's look on this stuff and we say, all right, so you don't like S stuff. Let's keep everything else constant. Okay? The other values, they're something. Okay? And you don't want to get rid of S. So what is happening right now? So you have E, you have S, okay? And you have some sort of a dependence of E over S. Okay. What value I do like, for example, temperature I do like. I don't like energy, entropy, but temperature I do like. Why? Because I have this equipment, it says thermometer, and I can stick it inside my sample and see how it varies. Okay? Entropy, I don't have an entropy meter, but I have a thermometer. Okay? So I'm going to say, well, yes, I'm going to change my variable from S to T. Okay? So what is T? T is dE to ds while keeping everything else constant. Yeah, but we already have kept all the other stuff constant. So this is fine. Okay? The derivative is what? We put a parallel line to our function at some specific s. Okay? Okay. So the slope of this line, the slope equals t, which is dE to ds. Right? And now Legendre made the following trick. He says, yeah, but E is defined not as a function of S, of T. It's defined as a function of S. You need another function. In order to perform your new quantities, new calculations, forget about E. You have to forget about E. Right? So T is only the slope. You cannot define the whole function. Right? You cannot define all the different points of E if you know only the slope. You need additional information. What is this additional information? Okay. So the point that it crosses the y-axis, let's call it f. Okay. So Legendre tells us the following thing. You have E and S. You don't want to describe E in terms of S. You want to describe E or the behavior of the function in terms of T, which is the slope of your function. Undoable. What you need to do is you need to add additional information. This information, for example, according to Legendre, and which is natural, is to say, well, the slope or this straight line crosses the y-axis at some point f, and I'm going to use this f. How I'm going to use this f? So I know the following thing. So if this is S, and this is E, so I know that T equals the slope of the straight line. This equals to E minus F divided by S. Great. So I have a definition, which is F is simply E minus T S.
Like the Lagrangian and the Hamiltonian.
Yeah, in some sense. Those are the conjugate variables. So f is a function of what? E is a function of s. F is a function of t. Okay. And this is Legendre transform. Because how do I know that it's as a function of t? Well, I can do the following trick. What is d of f? It is d of E minus T S, which is d E minus t ds minus s dt. But dE, we know what dE is. If all the other parameters or other variables are constant, so dE is TDS. TDS. We have minus TDS minus S dt. Eventually we are dF equals to minus S dt. So F is a function of, if E was a function of S, F is a function of T, and all the other parameters that were over here. V and then 1 and then 2 and etc. etc.
סטאס?
Yep.
מישהו מהבית שואל, שהוא רואה את זה כאילו ביוטיוב, הוא שואל שבעיקרון ההגדרה של הטמפרטורה שעלה פה זה בעצם דואי לדואס. הוא שואל מה קורה לטמפרטורה כשיש שינוי בעוד פרמטרים.
No, it is so the question is, temperature is d to the s. Okay, what happens to the temperature if there are other parameters involved? So temperature is the partial derivative of e to s when all the other parameters are kept constant. Okay? I hope at home it's clear now. Okay, so what is this f? So first of all, we know the following. We know that not only that f is a function of t, we know that df to dt equals minus s. df to dt, right, equals minus f. So the answer to the question, what kind of variables or what should I do if I don't like treating s or modifying s? The answer is you should forget about energy. You should define a different functional, a different function. And this function is E minus Ts. And this F has a specific name. It is free energy. You have properties of this free energy, and the variables of this energy is already not E, not S, but actually T and all the other variables that you have here. Now, this is a simple example of something which is much more general, and it's called a Legendre transform, and you, as mentioned, you already used it to find conjugate variables from Lagrangian to Hamiltonian, right? And it, in general, is defined as follows. So the motivation is, you have a function, you don't like the variables of this function, let's define another function based on derivatives, right? Based on derivatives of your original function. And then you can get something else where the variables are your derivatives that are called conjugate variables. Legendre transform. So if you have a function y, which is a function of x0, x1, and xn, and you define a different function, let's call it psi, which is y minus a sum k goes from j to n, p of k, xk, where p of k is dy to dxk. This is Legendre transform of y. Why it is needed? I already told you. I don't like the original variables, I want some other variables. What are the other variables? So first of all, this psi is a function of x0, because see what I've changed? I've only changed x case going from specific index j to the total index n. So I have x0, x1, xj minus 1, and then those variables, xj, xj plus 1, xj plus 2, they're already modified, and instead of them I have pj and pj plus 1 to pn. Moreover, d of psi equals to a sum of I goes from 1 to j minus 1.
From 0 to j.
Sorry, 0, right? 0. What are those? Pi dxi minus a sum k goes from j to n of xj, xk, dt. And we've seen it on a single variable, right? So you have this minus over here. When you perform a Legendre transform, you basically have a minuses for the different derivatives. And dot psi to dpk equals minus xk. This is the Legendre transform. Why do we use it? Because we want the same, we don't want to use energy. Because energy depends on some not really clear concept of entropy. And we want to use some other variables. Now, we already have defined f, which is E minus Ts. Okay. This is Helmholtz free energy. Okay. We can have G, which is E minus Ts minus PV. So what I'm switching over here, I switch from S to T, and I switch from V to P. Okay, this is Gibbs free energy. Who are Helmholtz? Who is Gibbs? Some physicists from the 19th century that decided to do this for the first time. Okay. And it's a function of T and P and whatever other particles. What else do we have? We also have H, which is enthalpy, which is E minus P V, and H is a function of S and P and all the other variables. And we also have psi, which is grand canonical potential, which is E minus Ts minus mu n. Sometimes we will use energy. Sometimes we will use Helmholtz free energy. Sometimes we will use Gibbs. Sometimes we will use enthalpy. Sometimes we will use grand canonical potential. The thing is that they all, in some sense, describe the same phenomena. The difference is that they use different variables. Okay? So if you know energy, you know all the other stuff. But sometimes it's more comfortable to use temperature and pressure. sometimes it's more comfortable to use temperature and chemical potential. It will depend on the problem, okay? And we'll see. Now, the last thing that I want to say, we know that there is a minimal energy principle. Minimal energy principle. What it says that at equilibrium, the energy is at its minimal value with respect to different unconstrained parameters. So I won't show it to you for all the different other potentials, so for all the different Legendre transformations, but you can say here minimal energy, free energy, Gibbs, enthalpy, grand canonical potential. Any Legendre transformation of the energy also has this principle of minimal value. It attains a minimal value at equilibrium. It doesn't really matter if you look on Helmholtz, on Gibbs, on enthalpy, or whatever you like. It will always attain a minimal value at equilibrium, so you can use or energy or all the other stuff. The only thing that matters, what are the variables that you want to work with? For some problems, entropy is comfortable. For others, temperature. And we will see, it will depend on the model, it will depend on different parameters of the system, which variables we would like to use. That's it for this week. See you next Sunday. כן. קונסטנט אנטרופי. מה עשינו עכשיו?
ב-free energy זה
בקונג'וגייט וריאבל. כן.
האנטלפיה זה לא משתנה.
האנטרופיה, כן. האנטרופיה
זה כן עצמי.
כן.
פרסקי.
אין אינטואיציה, זה טרנספורם לג'אנדר. כאילו, כל מה שיש לך זה אמרנו, יש אנרגיה, אנרגיה יש לעולם כי יספרו לך על אנרגיה מהתיכון, ועכשיו אתה אומר, תחשוב על זה, כאילו, כל האינטואיציה זה ש... לא אוהב לעבוד עם אנרגיה או עם זה, אז זה כזה, פרקטיקה, בדיוק, פרקטיקה, יש את זה. יש את הנקודה הזאת. מה זה אומר? זה אנרגיה שפחות טמפרטורה כפול, לזה אין לאף אחד אינטואיציה, ובזה זה מת. אני לא יכול להגיד, אני יכול להגיד, אנחנו נלמד את זה, כמות, לוג, מספר המצבים שיש רמת האי סדר, אבל אינטואיציה אתה לא תקבל, כאילו זה כל הסימות זה כמות הדרכים לאיפה שהמערכת יכולה ללכת ברמת ההתפזרות של האנרגיה במערכת. ואתה מחסיר את זה מהאנרגיה, שזה לא ברור מה זה, תקבל איזושהי משהו. זה מאוד נוח אז להרשים. כרגע זה... אנחנו נלמד מכניקה סטטיסטית. הדברים האלה ממוצעים. כל מה שאתה לומד בטרמו זה אתה... שאנחנו נגיע למערכות
זה יום שמח.
אנרגיה מיקרוסקופית ויהיה לך אנרגיה כללית של המערכת.
שנייה.
זה יעשה משהו לתוך המערכת בממוצע. בממוצע.
האנרגיה הקבועה בכל
פולימגנטי.
כי היא מערכת שכבר לא אקסטנסיבית, נכון? אתה זוכר שדיברנו על זה שטווח האינטראקציה הוא לא...
גם אתם שכחתם מטלאב ולכן...
הכל זה נשבע, ובגלל זה התחלתי. E1 שווה ל-E